Okay, in this video we're going to look at developing the gravitational concepts we were looking at in terms of gravitational fields and actually combining them with circular motion now. Because things aren't quite as simple as just dropping objects in space and then falling straight towards Earth. They're usually moving and we create orbits. So we need to look at spending some time looking at orbits now. So again, here's our Earth, which is going to be our big M for our mass. And say, for example, we have an object moving in an orbit. First of all, why does it move in an orbit? And what is an orbit? Well, technically, an orbit is just a constant state of falling. It's constantly falling. It's constantly falling because this object has a force acting on it in that direction. But because it's moving in that direction, we get this effect of circular motion. And if we draw other points on this, where you can see the force is acting directly downwards towards the center of mass, here we have the same thing again, but our motion is at right angles to that. Again, our motion is at right angles to the force, and so on and so forth. Well, where have we seen this before? Well, this is just circular motion. This is just circular motion in action. So this is having an attractive force pulling it in this direction. This is therefore now a centripetal force, and because it's moving in that direction, we have circular motion. So yes, this is anything that's in an orbit is technically constantly falling. It just doesn't lose any height because it's moving around the Earth at the same time. So we can actually now put the ideas of circular motion and Newton's law of gravitation together. So let's do that. So first of all, we have a force. That force is the centripetal force that's holding this in its circular motion. And we worked that out from last time as m omega squared r, to use the angular velocity version of this equation. Of course, there is a linear velocity, a linear speed version of this equation, which is mv squared over r, but we'll stick with this one for now. And that force is going to be equal to Newton's law of gravitation, which we saw in a previous video, which is gm over r squared. Well, quite nicely here, we can, first of all, we just need to make sure that we know what m's are which. Big M, the only big M in this equation is this one right here. Little m is the mass of the object moving around in a circle. That's this one and this one. So, as you can hopefully see, we can get rid of those by dividing both sides by m. So that gets rid of those. And we can also amalgamate the r's as well, because it's the same distance, r, as in the radius of the circle, the distance from that center point. So we end up with an equation which effectively is omega squared is equal to gm over r squared, r cubed, sorry. So omega squared is 2gm over r cubed. Our m is this m right here. As we well know, we can rewrite this equation to be omega is equal to 2 pi over t, but it's all squared. So we've got squared, squared, squared. So we can then change this 2 squared to be 4, because we know what 2 squared is equal to gm over r cubed. Which then lets us come up with, effectively, we are already there, but this is Kepler's third law. Now you might be thinking, well, what's Kepler's first and what's Kepler's second law? Well, we'll come to those in a later video. But for now, this is Kepler's third law. And Kepler's third law is effectively telling us that the square of the time period is directly proportional to the cube of the radius. And that is always the case. So we can rewrite this equation to show that nice and clearly as t squared is equal to, let's just write this correctly, so 4 pi squared r cubed over gm. And that, in a nutshell, is Kepler's third law. And you can see quite clearly here how t squared is directly proportional to r cubed, where 4 pi squared gm is a constant. Well, that's quite a nice constant, really, because 4 is constant, pi is constant, g is constant. The only thing you can ever really change in this is the mass, and that's the mass of the Earth. And I don't know about you, but the mass of the Earth ain't changing that much. So this value isn't going to change. So for all intents and purposes, this equation now quite nicely can be written t squared is equal to 4 pi squared over gm r cubed, showing that t squared is proportional to r cubed. Now this is one of those proportionalities that makes things come together, and we're hopefully going to utilize this proportionality in lesson.